Hello guys, in this video I want to show you how different drilling techniques are applied, and let us watch it.
This CD-ROM will introduce 12 of the most common drilling systems used for well construction. The variety of systems available exists because no one system can drill all formations and conditions effectively. Drilling systems will continue to evolve as new materials, products, and techniques are utilized to further improve the efficiency of well construction. It should be noted that drilling technicians should always adhere to safe drilling practices, which include wearing proper safety equipment such as CSA certified boots and headwear, as well as hand, eye, and ear protection. The Ontario Water Resources Act, Regulation 903, clearly details requirements for well construction. Drilling technicians are required to be thoroughly familiar with the content, procedures, and guidelines contained within Regulation 903, and to adhere to them carefully. Information supplied with equipment and products must be read and comprehended prior to starting any related work. The drilling systems profiled in this video all use one or more of the following 5 cutting actions, which are percussion, rotary percussion, rotary crush, rotary cut, and finally, rotary abrasive. The choice of the cutting action used is largely dictated by the geology of the formations to be drilled. For example, in soft clay formations, rotary cut is an effective cutting action. Rotary percussion, an ineffective cutting action. Cutting actions that require circulation of the flushing media, usually air-based and/or liquid-based, will utilize one of 3 flushing media paths, which are direct or conventional circulation, reverse circulation, and dual pipe reverse circulation. The circulation path for the flushing media is dependent primarily upon the drilling system used and the diameter of the hole. The volume of flushing media required is dictated by the rate at which cuttings are produced and hole diameter, whereas the flushing media pressure is influenced by the borehole depth and restrictions within the flushing media path. And finally, this video has been prepared to highlight the following drilling systems only, and as such, no attempt has been made to detail all aspects of each drilling system. Rather, this video will enable viewers to gain some insight into the characteristics of the various drilling systems used in well construction today. This project has been developed by Fleming College and has received funding from the Ontario Ministry of the Environment. The percussion method of drilling, cable tool, churn drill, sputter, or pounder as it's sometimes referred to, is one of the oldest cutting actions utilized in the drilling industry. Developed in China over 4,000 years ago, the cable tool is tried and true, responsible for millions of successful wells around the world. This system is still used today because of its own unique advantages, which include one-person operation, low equipment cost compared to other systems, simple, rugged design requiring minimal maintenance, low horsepower requirements of this rig, and finally, cable tools have proven to be virtually indestructible. These machines are mainly used today for drilling in unconsolidated materials and soft rock formations where relatively shallow depth wells are required, approximately 100 feet or less. Slow penetration rates are characteristic of this drilling system. Support equipment required for this drilling process are basic: a small truck with welding equipment, torches, and a small amount of makeup water. A separately mounted deck engine powers the rig. The cable tool uses the percussion cutting action, utilizing a 1,200-pound drill string and usually a carbide button bit. This bit goes up and down once per second, performing 4 important drilling functions at once: penetrating the material beneath the bit, reaming the sides of the hole, crushing the geology into fine particles, and mixing these cuttings with water. The drilling action, in conjunction with approximately 5 gallons of introduced water, mixes with the cuttings, which require bailing after approximately 4 feet of drilling. This flushing system requires the drill string to be tripped out of the hole and the bailer to be tripped into the hole. The bailer is simply a hollow tube with a check valve on the bottom, which fills with the cutting slurry mixture. The action of the dart valve enables the bailer to collect cuttings for ID and recording purposes, as per Regulation 903, as well as removing accumulating cuttings by dumping them in the mud spout. The bailer is also useful for measuring approximate water pumping rates and levels at any time during the well construction. The cuttings from the borehole are usually well mixed and small in size, representing an accumulation of the formations encountered since last bail. Cable tool drillers have developed the ability to interpret the feel of the drill string to improve well log accuracy and in identifying aquifers. The cable tool drilling process typically consists of drilling, removing the cuttings, identifying the geology, monitoring the water flow if present, and then advancing the casing. There are 2 methods for casing advancement: the drive cap and the drive blocks. The drive cap is primarily used by cable tool operators until such time as increased friction is encountered. The drive blocks then enable more energy to be transferred to assist with driving the casing down. The casing advancement continues in overburdened situations until such time as a suitable aquifer is encountered, or until the casing is firmly seated in bedrock, after which casing is no longer required, as the geology itself, or rock, stabilizes the hole. The large bull reel shown here supports the cable, which in turn supports the drill string. The speed at which it is turning here is typical of hole advancement in unconsolidated material. Ideally, casing is added in 10-foot sections to improve efficiency. Additional casing sections are usually welded, ensuring a watertight seal, as required per Regulation 903. The annular space between the working casing and the permanent casing is commonly grouted after borehole construction. The percussion cutting action obtains its striking energy from the drill string components, which consist of a 1,200-pound, 22-foot-long drill bar and the drill bit. The drill bar is fastened directly to the bit, which contains either carbide buttons or a hardened steel chisel face. This drill string assembly is lifted 22 inches and then dropped, allowing the bit to perform 4 important functions simultaneously. These functions include penetrating the formation beneath the bit, crushing the formation into small fragments, mixing these cuttings with the introduced water present in the borehole, and finally, reaming and maintaining the hole diameter in rock formations. The lifting and dropping sequence is performed once every second until such time as approximately 3 to 5 feet of material has been drilled, resulting in the introduced water being totally saturated with cuttings. The driller must then remove this mixture with the bailer, which consists of a hollow tube and a dart valve. The drilling cable supports the entire weight of the drill string assembly. The drilling cable is unique in its left lay construction. This unique feature imparts a clockwise rotation on the drill string during the up and down drilling process, ensuring an efficient cutting action and a straight, true borehole. The auger rig is commonly used in geotech and environmental drilling industries for both soil testing and groundwater investigations. The system shown is buggy mounted, but the same system can be mounted on trucks, tracks, or skids, based on the nature of the terrain they'll be working in. These rigs are usually powered by deck-mounted engines and are capable of extremely high rotational torque loads to the drill string. Due to the large surface area of the augers, these machines require significant energy in order to advance the hole. The support equipment is often self-contained or can include a separate vehicle which carries the supplies needed, including grouting materials. Due to the nature of this industry, operators may have numerous holes at one location, each of which may require grouting. Other equipment can include pressure washing equipment, needed to ensure no contamination occurs between holes or sites, as well as numerous other supplies required to perform the wide variety of drilling and monitoring operations characteristic of the auger rig. Auger sections are 5 feet long. The lead auger includes a pilot bit, which utilizes rotary cut action. The lead auger cuts the material, transferring the material up the flights of successive auger sections to the surface. No flushing media or drilling enhancements such as air, water, or fluids are used. This ensures true representative samples are obtained. Additional auger sections are stored on the machine and added as required. It should be noted that working around rotating augers can be very dangerous. Extreme care should be taken to prevent loose clothing or equipment from becoming entangled in the auger sections. Auger bolts are used to secure the sections together. Continuous soil samples can be obtained through the entire length of the borehole with the use of the split spoon sampler. The spoon is advanced ahead of the auger to ensure an undisturbed sample. 6-inch increments are marked off on the drill string. The standard penetration test uses either an automatic hammer or the cat head to lift a 140-pound hammer, which has exact travel of 30 inches. The number of blows required for penetration are recorded. The split spoon device then reveals a representative sample of the geology. The drilling and sampling continues until such time as the project engineer indicates that the monitoring well should be installed. Monitoring wells are installed with great care to ensure no physical contact with the supplies, protecting the integrity of the sample. Shown here is a section of the monitoring well flush joint casing. Note the black O-ring seal and fine slots, which permit only water to enter the monitoring well. The annular space between the auger string and the well screen is filled with sand to ensure sediment-free samples. The remainder of the annular space is now grouted as the auger sections are tripped out. Monitoring wells can be completed either using a flush mount cover or with an above-ground protective casing. Both finishing techniques facilitate ongoing water sampling. The bucket auger is used primarily in unconsolidated material for constructing large diameter boreholes ranging from 24 inches to 48 inches. These large diameter boreholes are ideally suited for areas producing low-yielding wells in aquatards. The drilling system consists of a truck-mounted drill with a separate deck-mounted engine, which must be capable of generating enough torque to overcome the friction associated with drilling such a large diameter hole. The support equipment required includes a service truck to carry the casing and grouting materials. 2 drilling technicians are required to operate the bucket auger drilling system. The cutting action is rotary cut. The bucket is rotated and advanced until it is full of cuttings, at which time it is tripped out of the hole, swung to one side, and a trip is released, emptying the cuttings onto the adjacent ground. Note that no flushing media is used, since the bucket auger removes the cuttings as hole penetration occurs. This produces cuttings which are clean, unmasked, and representative of the geology. This drill utilizes a large diameter table drive to rotate the telescoping Kelly, which in turn advances the bucket auger. Penetration rates are generally quite rapid in favorable conditions. During the drilling process, the hole may require the installation of temporary or working casing to stabilize the hole until permanent casing is installed. Drilling continues through the working casing, using a smaller bucket until such time as an adequate aquifer is located. The 4 telescoping sections of the Kelly bar enable the bucket auger to drill up to 100 feet in depth without the use of additional Kelly bar sections. The next step in this process is the installation of the permanent casing, which can be manufactured from concrete, galvanized steel, or fiberglass. Shown here is the installation of concrete casing using a tile setter. The annular space between the casing and the borehole wall at the aquifer area is filled with permeable material, such as gravel or washed stone. The well is grouted and developed to a sand-free state, as per Regulation 903. Shown now is a larger-than-average top-head drive conventional rotary drill, drilling a domestic water well in unconsolidated material. This system requires a support vehicle with a large amount of water on board to sustain the drilling process. The conventional rotary system is a 2-person operation, requiring significant capital investment. Ongoing maintenance costs for this rig are relatively high compared to other drilling systems. The rig is powered by the truck engine itself and requires significant horsepower and resulting fuel supply to perform the drilling operation. However, the conventional rotary drilling system offers excellent penetration rates, quick setups, and either rotary cut or rotary crush cutting actions. The rotary crush cutting action is being performed. The rotary drill uses the conventional or direct circulation path for the flushing media. The hydraulically powered drive end of the mud pump is shown, with the flywheel spinning. On the other side of the rig is the wet end of this double-acting piston pump. This is a closed circuit. The flushing media is pumped from the mud pit, through the suction line, through the pump, and discharged, either down the hole through the drill string, up the annular space back into the pit, or directly into the pit when mixing. The mud pit, through the use of baffles, helps to separate the cuttings from the bentonite mud mixture, as well as serving as a flushing media reservoir. The mud flushing media is composed of bentonite and water, which are mixed in the hopper prior to the drilling operation. This mixture performs 4 important functions simultaneously. Lubricate the drill pipe, cool the bit, clean and remove the cuttings from both the bit and the bottom of the hole, as well as control formation pressures. Accurate identification of the cuttings is made difficult due to the masking effect of the drilling mud. Larger cutting samples are more easily gathered. The smaller cuttings are contained within the mud mixture and are more difficult to identify. This particular rig has hydraulically assisted functions designed to minimize operator fatigue and improve efficiency. These include a breakout wrench, a powered fork, pipe spinners, and rod carousel. In the drilling operation shown, the operators first drilled a 6-inch pilot hole to identify the water-bearing zones, followed by the drilling of a 10-inch hole to allow for easy casing installation and grouting. In identifying the aquifers, care is taken to record the depth and extend the aquifer, as well as to ensure proper slot size required for screen installation. Drilling speeds vary widely depending on geology and hole diameter. The oversized hole is temporarily stabilized with the drilling mud. Casing installation usually occurs in 20-foot sections. Safe workplace procedures always entail the use of caution when working around heavy or rotating equipment. Never place yourself between something that moves and something that doesn't. Casing liners ensure casing sections are square to each other. Beveled joints provide for maximum weld penetration. After completing casing and screen installation, the hole is grouted and developed to a sand-free state as per Regulation 903. The most widely used cutting action today is rotary crush, since it is compatible with a broad range of formation types and flushing media. The bit construction is made up of 2 or more independently rotating cones, depending on its diameter. The smallest bit, or bicone, utilizes 2 cones, whereas the most common bit is the tricone, which is made up of 3 cones. Each cone on the bit is unique and is easily identified by its function. For example, in a tricone bit, cone number 1 drills the very center of the hole, while cones number 2 and 3 are each responsible for a different path or area. The length, size, and material the cone teeth are made from reflect the characteristics of the formation for which the bit is best suited. A long steel tooth is designed for soft, unconsolidated formations, while short tungsten carbide teeth excel in hard, consolidated formations. A combination of rotation energies and pull-down forces from the rig push the teeth into the formation. This, coupled with the rotating bit, results in a shearing, crushing action, producing cuttings which are cleared by the flushing media. The media utilized can either be air or water-based, depending on the formation types encountered and the capabilities of the rig. The rotary abrasive cutting action uses 2 of the hardest substances available for bit construction, namely diamonds, both natural and synthetic, as well as tungsten carbide. These materials are bonded to the bottom face of the bit only. The bit's body consists of a round steel tube. This hollow design enables the open face of the bit to cut 2 surfaces at once, the inside face of the borehole and the outside face of the core sample. To accomplish this, significant pull-down forces are combined with rotation speeds ranging from 1200 RPM to 2000 RPM. These forces are applied to the face of the bit by the swivel head. The water is injected into the rotating drill string to cool the bit and flush the cuttings up and out of the borehole. These cuttings are quite fine and have the consistency of flour. The core sample is contained within the inner tube and is stripped out for evaluation purposes at the end of each run. The dual rotary drilling system represents one of the more recent advancements in drilling system technology, being especially well suited for drilling in unconsolidated material, such as overburden, glacial till, cobbles, and gravel. As the name implies, the dual rotary system utilizes 2 heads to simultaneously advance the hole and the casing. A lower rotary drive rotates and advances casing, while a carbide shoe enables the casing to cut its way through the formation. The top head drive drills inside and ahead of the casing. Once the desired casing depth is reached, the dual rotary rig continues drilling, much the same way as a conventional top drive air rotary drill. The dual rotary system is a 2-person operation that can use either rotary cut, crush, or percussion cutting actions. Shown here is the rotary crush cutting action. This system utilizes a conventional circulation system with water and air as the flushing media. The large metal bin is being used on this job site to contain the cuttings. This keeps the new well location pristine and as undisturbed as possible. The bin will be removed when drilling is completed. The drilling technician collects cutting samples of the formation at the discharge. These samples are clean and representative of the geology. and facilitate proper record keeping as per Regulation 903. These rigs can be expensive to operate and maintain. However, the dual rotary rig can drill through any formation, producing straight boreholes and excellent penetration rates. This system is also relatively easy to operate compared to some of the other drilling systems in use. The power for the drilling operation is provided by the truck engine itself. Separate support vehicles include a significant amount of water, as well as the usual welding and cutting equipment. Other support equipment includes a knuckle boom crane, grouting pump, and water injection pump. The reverse circulation drilling system is quite unlike any of the other systems profiled, in that it is a very large rig, requiring a big footprint for both the rig itself as well as the machine-dug settling pit. These rigs are primarily associated with drilling large diameter wells in unconsolidated material, ranging from 24 inches to 50 inches in diameter and up to 1,000 feet deep. The cutting actions used in the reverse circulation system include the rotary cut and the rotary crush actions. Shown here is rotary cut. The unique direction of the water-based flushing media is profiled. This fluid is sent down the annular space between the drill string and the borehole, removing cuttings back up the drill string and into the settling pit. This pit must be very large to accommodate a sufficient amount of fluid, which is required to flush the large amount of cuttings generated in drilling a borehole of this diameter. The excavated material needs to be replaced with fluid as drilling continues, further increasing the quantity of fluid required for this drilling process. In addition to the makeup fluid required, a significant amount of fluid is displaced and lost in the original formation, as this system does not typically use bentonite and therefore does not entirely seal the hole during drilling. While increasing the demand for liquid used during borehole construction, this system has the advantage of reducing development time as compared to traditional mud rotary drilling. The dual-wall reverse circulation rotary drilling system is primarily used in mineral drilling exploration, where accurate chip samples of the geology are required. While not typical to well construction, it may be used in remote locations or where more suitable equipment is not available. This system utilizes rotary crush and rotary percussion cutting actions, offering fast penetration rates and clean representative samples. Unlike the diamond drill system, where operators must trip out of the hole to secure the sample, the dual-wall reverse circulation system provides continuous samples as hole advancement occurs. Calculations of the drill string, hammer, and bit lengths enable operators to accurately record the drilling depths from which the samples are obtained. The main flushing media is air, but water or water and foam may be added to enhance the flushing of the cuttings. The dual-wall reverse circulation system produces clean, representative cutting samples. The unique features of this system are the bit, dual-wall drill string, and circulation path of the cuttings. In conventional down-the-hole drilling, the exhaust of the bit pushes cuttings back up the annular space between the drill string and the borehole. However, dual-wall reverse circulation drilling systems pass the cuttings internally, up the center of the drill string to the surface, where they are collected for analysis. This is achieved through the design of both the dual wall and the drill bit, which has special channels to enable air to travel through the bit. These channels enable flushing air to travel down through the bit. The chip samples are removed through the two large holes located on the bit's cutting face. The hammer has an oversized chuck which seals the hole behind the bit. A collection unit is normally used to gather cuttings. In this video, it's been removed to properly highlight the volume of cuttings produced and the air flushing media being used. The drilling process continues until such time as an additional section of drill string is required. The dual wall casing's outer sleeve permits flushing air to travel down the string to power the hammer, whereby the inner cavity returns the cuttings back up to the collection unit. hole diameters typically range from 3.5 inches to 10 inches and can be as deep as 2,000 feet. These rigs are typically expensive to purchase and maintain, but offer an economical solution to geological sampling needs as compared to the diamond drill. The differences between the air rotary system and this drilling system are primarily the cutting action and the resulting cuttings as shown. The down-the-hole hammer uses the rotary percussion cutting action through the use of a button bit. This system is best suited for well-consolidated formations, offering excellent penetration rates. Compressed air provides the percussive energy to power the hammer. The resulting exhaust removes the cuttings. Note the quality of the cuttings. They are large, clean, and unmasked, representative of the geology. Water only is added to the air to assist with both cuttings removal and suppressing dust. This results in an aquifer, which requires minimal time to develop. The following example utilizes a chalk line to show the correlation between penetration rates and drill string rotation. This example is relevant to a 6-inch hole diameter only. First, too slow rotation for the geology is represented by the wide spacing between chalk lines. Next is correct rotation speed, as shown by approximately 3/8 inch spacing between chalk lines. Finally, excessive rotation speed is shown, as noted by minimal spacing between chalk lines. The diamond drill is not typically used in water well construction, as it is primarily for mineral exploration in hard rock formations or, in some circumstances, monitoring well construction. However, this system can be used to construct water wells in remote areas where no other suitable equipment exists. The disadvantages include a small diameter hole with small reservoir that is not well suited to pump applications. The components of this system are designed to be broken down into 1,200-pound modules to facilitate transportation into remote areas. These modules or components include a diesel engine to provide power, the drawworks, which facilitates tripping in and out, the swivel head to provide feed and rotation to the drill string, and the water injection pump to assist with the flushing of the cuttings and the cooling of the drill bit. The same cutting action is used for advancing the hole and the casing. This rotary abrasive action is achieved through high rotation speeds and pull down or thrust forces to enable the diamonds in the bit to wear away the rock. This results in relatively slow penetration rates as compared to other drilling systems. And very fine cuttings. The drilling process continues until the inner tube is filled. Shown here, the technicians are drilling in 2-foot increments, as represented by the stroke of the swivel head. This 2-foot stroke is repeated 5 times until 10 feet of core sample has been collected in the inner tube. However, some diamond drills are capable of a 5-foot, 10-foot, or even longer stroke. The inner tube is tripped out by removing the water swivel. Lowering the overshot down the drill string to the inner tube. This allows the inner tube and core sample to be retrieved. The core sample is then carefully packed into a core box for future analysis. The drill-through casing driver system is well suited for drilling in unconsolidated material, offering excellent penetration rates, especially in conditions that present lost circulation problems, such as cobbles and gravel. This system advances the casing at such a rate that the time required to weld casing sections may exceed the time to install these sections. The system utilizes conventional circulation with air flushing media. Shown here is a top-head drive machine advancing the casing in unconsolidated material. The rig is demonstrating rotary crush cutting action, primarily because of the geology expected on this site. However, this system can also utilize rotary cut and rotary percussion actions. Support equipment for this drilling system includes a support truck with a large water reserve on board. In addition to welding equipment, the rig also includes an air compressor, which is used to power the casing driver, as well as act as a flushing media. The truck's engine is used to power the rig through a transfer case. All systems are hydraulically powered, with the exception of the air-driven casing driver. 2 technicians are required to operate this drilling system. The drill-through casing driver system is unique in its ability to both advance the hole and casing in one operation. The rig contains a casing driver head located below the rotary head, enabling the advancement of casing to directly follow the drilling of the borehole. New sections of casing are prepared with the drill string sections inside and are hoisted and mounted into position together. Air is utilized to flush the cuttings. Water is being injected to enhance the air's ability to remove the cuttings and control dust. The water is pumped from the support vehicle through an injection pump, down the drill string, through the bit, and back up the inside of the casing to the casing driver, and then out onto the adjacent ground, where the technician can obtain samples which are very representative of the geology encountered. In this particular well, the grout was installed between the oversized working casing and the finished casing, then enabling the working casing to be removed and drilling to continue. The technicians drilled approximately 4 to 5 feet ahead of the casing, and shown now is the casing driver rapidly advancing the casing. Drilling of the borehole then continues in the stabilized hole. The order of operations for the drill-through casing driver is drilling the borehole, advancing the casing, adding a new section of pre-assembled casing and drill rods, welding the section to the previous section, and then advancing the casing section. This drilling sequence is continued until such time as suitable aquifer is located or bedrock is encountered.
Hello, dear my subscribers and video followers. If you get this video is important for you, please subscribe, like and share. This is important for the next video to be notified for you. Thank you.